So the lab you guys are going to do this week is the preparation of an alkene. Alkenes in general have kind of a not so pleasant smell, so we're going to kind of build our apparatus to contain that smell as best as possible. So just be aware of that. Try and keep all your work in the hood so that way you can prevent stinking up the whole lab, and then we can survive better. So this is again another or probably one of your first synthesis labs. So we'll kind of go through the general idea on what you should be doing for every synthesis lab. So it can be kind of broken down into roughly 5 parts: the preparation, the reaction itself, what you're doing in lab, isolating your compound, identifying it, and then wrapping everything up and concluding it. So that's kind of the overall picture of what a synthetic chemist would do. Okay? As part of the preparation for this lab, you need to understand what's happening with the reactions. So you can go through and look at your starting material and your product and try and evaluate what changed, how it changed, why it changed, all that kind of fun stuff, which is ultimately looking at mechanisms. Okay? So for that first one, you guys have already seen that one. What occurred? What changed? Anything change? Okay, you actually pointed out several changes there. We went through, the carbon-iodine bond broke, and you said it was replaced by the carbon-chlorine bond. So by going through and marking what things changed, you can start to come up with an idea with what type of reaction or how it occurred. The rest of that structure was completely irrelevant. When it comes to your exams, we'll give you big, long, drawn-out structures. The only reason they're there is to confuse you. Focus in on where the chemistry is occurring and only that chemistry. Ignore everything else. Okay? So we could go through and classify this as a substitution reaction. The iodine was substituted for the chloride. Okay? Now what we're going to do is move into a slightly more difficult reaction, which a lot of students seem to have problems with, or at least identifying the pieces that changed. What happened in the second reaction? Again, try and be as simple as possible. Think about the bonds that were broken and think about the bonds that were formed. So what changed? I heard, what are you saying? We broke that carbon-iodine bond. What else happened? We formed the double bond. Those are the two, what I would refer to, easiest answers to look at. But is that all that happened? Whoops, sorry. What about this H plus floating around out there? Seems awfully suspicious that it all of a sudden just appeared. Okay, where did that H plus come from? There is a bond right here to a hydrogen. And in fact, if we count all the hydrogens at that carbon, we'll have 2. So we've got implied hydrogens there. If we go to that same position on the alkene, how many hydrogens are there? Only 1. So where did that H plus come from? Came from our original alkane. Not going to be easy to draw a line through. Okay. We broke that bond as well. Okay. So recognizing where things are shifting from, where they're breaking off of, you've got to be able to see those patterns. And if you can't see them, draw on the atoms that we imply. Okay? So remember way back when we showed you slides on what simplifications happen in organic chemistry. I would highly recommend that when you work problems, you hold those simplifications near you or you have them handy. Okay? One of them was that we implied hydrogens. Every point is a carbon atom. And then we often imply lone pair electrons. Okay? If you don't keep those in the back of your head as something that's constantly going to be happening, you're going to oftentimes forget each of those pieces, and in this case, you might lose that hydrogen and then start to get lost and make things up as you go. Okay? So try to find and identify these things as we function with it. We could go through and take a closer look at this. If we combined H plus and I minus, because they aren't particularly stable necessarily things on their own, we could put them together and we get the molecule HI. Okay? It's also a small molecule. Taking a step further, what we're looking at in this reaction is an elimination of a small molecule. You'll see different names given to these: dehydrations, dehydrohalogenations. They're all ultimately eliminations where you've lost a small molecule. One of the other side reaction, or one of the other results of an elimination reaction would be the, what else do you see change here? It is obvious, we already stated it. You get the formation of that double bond. Okay? So recognizing these patterns and what's happening can help you out a lot. Okay? We're also adding a new level to this chemistry, or this version of the chemistry, by changing the functional group that we're going to start with. Instead of dealing with an alkyl halide, which we saw last week, we're now going to bump it up to alcohols. Okay? As far as the material that was covered so far this semester, you looked briefly at alkanes, and you could look at their intermolecular forces, which were your London dispersion forces. And the only thing that you were really taught about alkanes was that they had low melting points and low boiling points. Why would they be so low? Oh, what? Right, general idea. We're all looking at covalent bonds, no polarity, no partial charges, which means there's no reason for them to interact, and we end up with very weak intermolecular forces, the London dispersion forces. Okay? Well, because they have such low, or a secondary feature of them having low boiling points also suggests that they're also very unreactive. Okay? If we then up the reactivity a little bit, we could add a chloride, exchange a hydrogen for a chlorine. Okay? What's different between chlorine and hydrogen? Is there any difference between chlorine and hydrogen? We get size. What else? Electronegativity. Okay? Chlorine is much more electronegative, meaning it draws a lot of electron density out of that carbon, which means what happens to the carbon? The carbon starts to become positive, and our chlorine was partially negative. Okay? Because we've now got partial charges, individual molecules are going to start to have a stronger attraction to each other, which means our boiling points and our melting points go higher, because there's now a stronger attractive force holding those individual molecules together. Okay? We can take it a step further and start to look at their reactivity. How can that molecule interact with other molecules or do changing of chemical bonds? And what we ended up finding was we had an electrophilic carbon, meaning that carbon lost electrons, and because it's lost electrons has become opposite of negative would be positive. Okay? If it's become positive, it wants electrons, or it becomes electron-loving. We're looking at electrophilic. Okay? That was pretty much the only chemistry we could get out of the alkyl halides. When we shift to alcohols, we're now, instead of using a halogen, an oxygen. Well, what do you know about oxygen versus halogens? Are they electronegative? Yes, so oxygen's still really electronegative. Okay? It's a little bit smaller than chlorine. Okay? But it's really, really electronegative. So we would predict and expect that we'd get the same typical results. That carbon is still going to be electrophilic, okay? Because we still have a very electronegative element attached to it. Okay? What else can change in this structure? Is that the only thing that was changed? You mentioned it. What'd you say?
Hydrogen bond to the oxygen.
We've got a hydrogen bond to the oxygen. So not only are we changing the structure by adding an oxygen instead of a halogen, but we now also have a second atom added as well. We've got that hydrogen in there, okay? Which does a couple things for us. One, the first and foremost, hydrogen bonding. We now get a very strong intermolecular force, which means if we compare similar structures, our melting points and our boiling points get even higher because we have that strong force. Okay? We just looked at that electrophilic carbon. That's great. Okay? But that oxygen now does other things as well. The chlorine couldn't really share its electrons. It's only really happy with one bond. Oxygen, on the other hand, can share some of those electrons. So it can become nucleophilic. So by making it an alcohol, we've now added a nucleophilic oxygen, another site for reactivity. Taken a step further, if it's a nucleophilic oxygen, meaning it wants to give its electrons to a positively charged atom, that atom could possibly be a hydrogen ion. Well, if it donates its electrons to a hydrogen ion, what have we made? How would you define that oxygen? It's a base, a Bronsted-Lowry base, okay, which is what's underneath that writing. Okay? That hydrogen is bound to a very electronegative element, in fact, oxygen, which means that hydrogen can also be acidic. Okay? So a simple change to the structure drastically changes the amount of reactivity that we could potentially pull out of this molecule, changes a lot of things for us. So it opens up a lot of doors as far as what we can do with that structure. Okay? If we're now going to compare the reactivity between the alkyl halides and alcohols, okay? If we take a look at this reaction, okay, what type of reaction is shown in both of these cases? What does Nu stand for? A nucleophile. Okay? What is that nucleophile doing? It's exchanging its position with X, also known as substitution. So we've done some kind of nucleophilic substitution. Did we do it in one step or two steps? One step, because all the arrows are in a single step, which means which type of mechanism? SN2. Okay? You'll notice in that second part when we're looking at the alcohol that we say that reaction, that substitution does not actually occur. Okay? Even though we would have expected or maybe predicted that due to all of those differences in electronegativity. But there's another feature that comes out of this. What we end up generating is hydroxide as a leaving group. Okay? If we were going to look at, say, a standard halide, let's do chloride. Chloride versus hydroxide. Which one would you rather have splashed in your face? Remember, the last time you cried salt, right? What's in salt? Chloride, right? So when you cry, sodium chloride is washing all over your face versus sodium hydroxide. Which one is more unstable? The hydroxide. Okay? Which means we don't want hydroxide. Hydroxide is ridiculously reactive. So as soon as it forms, it immediately goes back and starts to react a second time, pushing us the wrong direction. So we end up not getting a reaction. Okay? We briefly talked about leaving groups. In theory, your lectures talked about them in a lot more depth. But as a general rule of thumb, a good leaving group is one that is able to stabilize the electrons it's taking with it. Okay? How can it stabilize those? Resonance, electronegativity, all those fun rules. Okay? Typically, they are really, really weak bases. If it was a strong base, what does that mean about its reactivity? It's highly reactive. If it's highly reactive, is that a good leaving group? No, it's the complete opposite of a good leaving group. We want our leaving group to be stable. Okay? That's why alcohols often require an activation step, if you will. A pre-reaction before they can officially go through your substitution or elimination reactions. Okay? We said that oxygen wasn't very good, so what we can do is evaluate that oxygen or that new bond, the oxygen and the hydrogen, and see how we can change and manipulate that so that it is more stable. So we can take advantage of the acid-base characteristic of those two pieces. Okay? Before we start looking into the mechanism of this reaction, okay, based on what I saw in the morning class, you guys are really unfamiliar with resonance mechanisms, how to move arrows, all that kind of fun stuff. So this is why this is up here as kind of a general review. Okay, on the left, we're looking at the rules for resonance. On the right, we're looking at the rules for mechanisms. Okay? Always, 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 when we're moving electrons, we'll always move them from a source to a lac. Curved arrows show the flow of electrons, not the flow of atoms, which is the hardest thing for people to understand and use appropriately. Okay? So you need to move electrons, not the atom. The atom will follow the electrons. Okay? So be careful with that. I'll let you review those rules later on. Okay? So if we're going to evaluate our elimination in lab, okay, one of the things that we need is that leaving group, our OH, to leave. And we said it can't leave on its own, so we're going to have to evaluate the chemistry of that oxygen and hydrogen first. Okay? So let's take a look at, say, that oxygen-hydrogen bond. Okay? So if we draw that in, so we're all looking at the same thing. Okay? If I evaluate that bond, where are those electrons spending most of their time? On the oxygen. So we could go through and say, heck, maybe to activate, the hydrogen becomes acidic. Well, if the hydrogen's acidic, it leaves as, it's removed as H+, which leaves what behind? What's left on the oxygen? Electrons. What happens to its charge? Becomes more charged. Okay? It becomes negative. Is a negative thing going to be stable leaving? No, it's already unstable. We've completely removed all ability for that atom to act as a leaving group. So instead of looking at the hydrogen, what we're going to do is evaluate the oxygen and try and make that more reactive. So what we're going to react it with in this case is an acid catalyst, which is going to supply H+. Okay? Oxygen happens to be a decent base. It's going to share its electrons. So I'm going to show an arrow between the oxygen and the hydrogen. Oxygen is my source. I start my arrow at the source and I end it where I'm lacking electrons, at that hydrogen. Okay? I've done a single step here, so now what I will do, draw my arrow and draw the product of this. That's not an eraser. So what's the result? Did I do anything to the ring? Nope, so we'll draw it on there. Did I do anything to that hydrogen floating up there? Nope, so we'll also draw that on there. Did I do anything to that oxygen-carbon bond? No, there's no arrow shown to it. Did I do anything to the oxygen-hydrogen bond? The one that was already there? No. What have I changed? I've added one more bond. What happened to that oxygen, or what's that oxygen now? What's the problem with it? It's positively charged. How do we know it's positive? So we could have memorized our significant bonding patterns, or we could evaluate the structure. Oxygen is in the reactant. Is it charged? Do you see a charge next to that oxygen? No. Which means, what happens when we move to the product? What's happening during our reaction? It's sharing its electrons or losing them. If it starts neutral and it loses electrons, what happens to it? It's going to have to become positive. Okay? Does oxygen want to be positive? No, so what's it going to do? It's going to have to grab electrons from somewhere. Where's the closest source of electrons to that oxygen? Any one of those bonds. Which is the easiest bond to pull electrons from? Which atom's more electronegative, carbon or hydrogen? Carbon. So which bond is easier to remove electrons from? The hydrogen, which means what happens? The reverse reaction. We've got an equilibrium reaction occurring here. Okay. Does that progress us towards our product? No. What's the difference in electronegativity between carbon and hydrogen? Are they really all that different? No. So let's take a look at the other option. Let's say that oxygen takes the electrons away from the carbon. Where should I end my arrow? On the carbon or the oxygen?
Oxygen.
Why should I end it on the oxygen? Because it's positively charged. I want to draw my arrow starting from the electron source, which is that bond, and move it to where it's lacking, that oxygen. Okay? What's the result of that? Try and draw as fast as I can. Our carbon is now positive because it lost electrons, and we've got H2O floating around. That carbon being positive, is that a particularly good thing? Is that a stable thing? Let's try that. No. So we need to stabilize that positive as best we can. How can we stabilize a positive charge? We need to give it electrons or give it something negative. Where's our closest negative? Again, I'm probably going to give you the answer you weren't expecting. Water. Water's got electrons. Those electrons could come back, meaning which way does our reaction go? Backwards. Okay, so again, that's not very productive. So what we wanted to do is see what other sources there are for electrons. Don't draw this, by the way, if you're about to draw this. Where are there other electrons? How about this bond? A nice little green bond. Okay, there are electrons in that bond, aren't there? Is that a good source of electrons? Why would that be a bad source of electrons? What happens if we took the electrons from that bond and gave them to the carbon? The ring is broken, which isn't necessarily a bad thing in this case. Okay, why is it unstable? What happens to the carbon? What happens to that bottom carbon? Started neutral and it just lost electrons, which means it's positive. So we trade one positive for another positive. Okay? We could evaluate that further. Our first positive, the structure that's up there, is a secondary cation. If we broke that bond, we'd have a primary cation. So not only is that not productive, it takes us in the wrong direction. It makes everything more and more unstable. So we need to find electrons somewhere else. So we could move to the next atom out, or the next closest source of electrons. Instead of going to the bond, we could go to the atoms. Well, if we take electrons away from an atom, that's the same kind of situation. That's not particularly happy either. Okay, those electrons were located around the atom for a reason. We want to then shift even further away to the next bond out. And in that next bond situation, we can look for what can be referred to as beta hydrogens. Okay, because they're the second position away. In that bond, what do I have? I have electrons. So I can take those electrons and share inwards to form my double bond. What happens to the hydrogen? We'd have H plus and we'd have our elimination product. Okay? So the idea is to follow the arrows, follow the reactions, look for chemistry. You're finding electrons, you're finding a lack of electrons, and you're just pushing them around until something productive happens. Okay? One of the things that's nice about this type of situation is what we're dealing with is a starting material and a product. All you have to do is find out how to get there without breaking any rules. Okay? So if we go through and look at each of the individual steps, our first step is our acid-base reaction, which is almost an activation. We're activating the alcohol so that it can leave. If we move to the next step, we're looking at an elimination. We would call this an E1 reaction. Why is it an E1? What is this species right there? A carbon that is a cation, also known as a carbocation. Where have you seen carbocations before? How? During class. How about an SN1 mechanism? Okay? The E1 and the SN1 mechanisms directly compete with each other because they follow the same general rules. Okay? So if we form that carbocation, that's a red flag for a 1-type mechanism, which means unimolecular. We get SN1, we get E1. Okay? Our last step would be the actual elimination step, where we end up forming our hydrogen, forming our double bond and our hydrogen ion is kicked off. Okay? A couple other things that we could mention here or look at. We have that carbocation. How could we make this reaction go faster? How about if I'd had a methyl on that carbon as well? Would I expect my reaction to go any faster? I think I heard a yes, but that might have been in the hallway. Why was it a yes? No. Evaluate the carbocation. The carbocation formed in that intermediate, if we make an extra methyl there, is what kind of a carbocation? How many carbons are attached to it now? 3, which means it's tertiary. The more stable our carbocation, the more likely the reaction is going to occur. Okay? The rest of this will be fun. I kind of have to whip through it. Double bond stability. So in an elimination reaction, we could potentially see multiple types of double bonds formed. If we get multiple types of double bond products, we've then got to evaluate the stability of each of those products and decide, is one better than the other? Okay, so if we take a look at the structures drawn up here, is any one of these more stable than any of the others? Tetrasubstituted is more stable. Why? What makes each of these structures reactive? What did I say the first thing you should be looking for whenever you're looking for chemistry? Electrons. Where is the easiest source of electrons in each of these structures? What's that? In the pi bond. So we're going to want to take, good, I didn't do it. Take the electrons out of that pi bond. For them to come out and react, they have to pass the rest of the structure. So if we take those electrons and try and go out this direction, what do they end up seeing? A methyl group. What is a methyl group? CH3. What's in CH3? Opposite of protons. We've got a lot of electrons out there. What happens when the electrons of that pi bond get near the electrons of the CH3? They repel away. What happens if we go this direction?
Doesn't need them. Doesn't want them.
Doesn't, what do you mean doesn't want them?
It doesn't want that bond's electrons. It doesn't want those electrons because it's already happy.
True, but what we're trying to do is get the electrons out of the pi system, have them react with something else. And in the case of the tetrasubstituted situation, those electrons are buried within the structure. The CH3s block the electrons from the pi bond going out and reacting. If we move to the tri-substituted, what happens if we move the electrons this direction? Okay, now we see a hydrogen, which, yeah, that's a bit, does have electrons, but does it have as many electrons as, say, a CH3? No. Okay, which means the tri-substituted is going to be more reactive because those electrons can pass by the hydrogen a lot quicker and a lot easier than they can by the CH3. The same applies for all of these others. If we look, we can move those electrons out past the hydrogen a lot easier than by the methyl. So as we reduce the substitution, we end up becoming more and more reactive. Why do we call it tetra, tri, and di, and mono, all that? We'll look at the groups attached to the double bond. If those groups are not hydrogen, we count those as a substituent. So in the case of that first one, we've got 4 methyls, tetrasubstituted. Why does this become relevant? Well, we're always going to produce the most stable product. Okay? A guy named Zaitsev happened to see this and decided to claim this rule for himself when it came to double bond chemistry. It's not different than any other version of chemistry. We're always forming the most stable bond or the most stable structure. It's the goal of all chemistry. It just so happened that he was the first one to see it and predict it for double bond chemistry, and he got his name attached to it. So we're always going to try and make that most substituted double bond. Okay? There is one exception which you might see in lecture. I'm not going to spend any time talking about it. The elimination reaction, this is kind of how I would break down the individual steps of the experiment into the very simple parts so that I know exactly what I'm doing. Ideally, you should be doing this before you get into class, so you've got a general idea so you can get through it faster. Okay? Is there anything that we could take advantage of? Well, we could go through and look at the intermolecular forces for each of these compounds. The intermolecular forces for our starting material is going to end up coming out to be hydrogen bonding. What do we get for the product? London dispersion forces, or LDF. Which of those is a stronger force? Hydrogen bonding. What does that mean about the physical properties? What would we expect for the melting point or boiling point of our starting material? We would expect it to be higher. Both your product and your starting material are liquids. So what we're going to do is take advantage of the difference in intermolecular forces, and we're going to separate these liquids via distillation. Okay? Your boiling point is the point at which vapor pressure of the liquid exceeds atmospheric pressure. Okay, so that's your definition of a boiling point. If we took a look back at our reaction, which compound would most likely be a gas? Starting material or product? Product, because it had a lower boiling point, which we could look up or we could evaluate just based on their structure. As far as the apparatus goes, you need to use your conical reaction vial, not the storage vial. Can anybody tell me the difference between these two vials? The top. Okay, your storage vial has a polished glass joint. The reaction vial has a powdered glass joint, or frosted. The storage vial is probably the most dangerous piece of equipment in your drawer, particularly when they put it together wrong, because sometimes it sort of fits with your glassware. And that sort of fit usually means that the TA has to deal with hot, boiling organic materials bubbling out the sides because you attempted to screw it all together and got half close. Okay? So please don't use the storage vial. Use your reaction vial when starting this experiment. Okay? The next... Whoa. Why did I do that? Next piece of equipment is going to be a Hickman distillation head. As we boil and heat the solution, we're going to turn our product from a liquid into a gas. If we don't have anything above our reaction vial, where's that gas going to go? Into the atmosphere, ultimately our lungs, not a particularly happy place for it to be, or worse, in our nose where we can smell it. Okay? So what we want to do is try and trap that, both for our sanity and for our product yield. And what we're going to use is a Hickman distillation head. This thing is built to get your vapors up away from the heat. Well, if it's up away from the heat, what happens? Very simple observation. It condenses, which is the harder observation. It cools. There's no heat. Well, if there's no heat, our vapor becomes a liquid, condenses, drips back down, and there's a little bulb at the bottom of this, okay, where your liquid will collect. You can then unscrew the side cap and pipette the liquid out that side, okay, as your reaction's going. By the way, if you happen to look in at that side cap and you see red, then your system was put together wrong. Ask Robin or Stephanie, and they will help direct you to get that fixed so it's not put together incorrectly. We're going to be extra careful about vapors, so what we're also going to add on top of the Hickman distillation head is a water-jacketed condenser. Its role is to now add cold water to help cool and condense things. Air sometimes is not the best cooler or the best cooling solution, so what we'll do is add a little bit of water. That water is going to run outside our condenser, cool or help the vapors condense and drip back down in. Water always goes in the bottom and out the top. As if that wasn't enough, we're going to further try and trap the vapors by adding a drying tube. Okay? This is going to get packed lightly with cotton and then a little bit of drying agent, which is going to help soak up any kind of nasty smells coming out of this. Okay? That's its ultimate goal. This one provides the best image of the cap assembly, which absolutely has to be put together properly. You've got the ground glass joint, and then you've got the rubber O-ring and the screw cap. What's the point of the ground glass joint? What's that?
So you can make a hard seal?
Yeah. The ground glass joint makes your airtight connection. It prevents liquids from coming in, it prevents airs from coming in. It's nice, it keeps that set up. However, if we look at the extended apparatus, we've got a lot of pieces of glassware all the way up there. Okay? And because each of those is an individual piece, we would have to clamp it in case we knocked it. We don't want all those things falling apart. You'll notice at each of those joints that we've got a cap. That cap is exactly what we've got over here, and underneath it you have the O-ring. And what that's there for is to actually keep glassware together. And I'm not going to write all that up. To get, how about that? Its goal is to kind of keep those two pieces together so they don't come apart. If you've put it together properly, you should not be able to remove the two pieces of glassware away from each other. Okay? So it's a nice little safety piece that'll help out with clamping and dealing with your glassware. Okay? Now what we can do is run it all together. We can put it all together. Beautiful, right? Nice little animation. I spent a lot of time on that. Okay? Okay. I'm not going to do it again, though. So cyclohexanol has a higher boiling point, so what we'll do is go ahead and distill our stuff across. Unfortunately, one of our byproducts, water, is also going to distill across. So you're going to end up with a container that contains two solutions. You'll have water and 4-methylcyclohexene. Both of those are liquids. How would you be able to separate those liquids away from each other? Boiling point didn't work. Extraction and close on the different densities. Something a little bit more important. Nonpolar versus polar. If we look at 4-methylcyclohexene, it's a nonpolar molecule. Would we expect that to be soluble in water? No. Now we can evaluate the densities. The 4-methylcyclohexene, I'm pretty sure, is less dense than water, so it will rise to the top. You can then pipette out the bottom layer, and you'll have your product. What was that?
That looks gross.
Yeah, we'll talk about that. Anybody recognize what that picture is? What's that? Maggots? No.
Looks like maggots on sand.
It's rice in what? In salt. Okay? First time I ever saw this, I thought it was maggots too. I thought it was really weird. Like, why are maggots eating salt? There are some people that will keep rice in their salt shakers along with the salt. Why would you do that? It absorbs the moisture. Well, why do you need it to absorb the moisture? What's going to happen to the salt if it absorbs moisture? It starts to get stuck. It clumps up and it forms a big chunk that we can't shake out of the salt shaker. So what we're going to do to remove our water is first pipette, remove the bulk water, the easiest water for us to see, what I would refer to as the visible water. The drying agent's going to take care of the invisible water. Okay? By the end of this step, you should have a clear liquid. Okay? That does not mean that it's dry as you might envision your clothes. Okay? What we're looking at is the loss of water, not of liquid. Okay? How would you know that you've added enough drying agent? It'll be dry. How do you see it's dry? Because it's still a liquid.
You say it'd be clear?
Okay, you should expect to see it go clear. That can be helpful. No, because it's not visible water. What happens if there was water? Other way around. It's going to clump around the water. What happens if there was no water? It'd stay the same. It's not going to clump because there's no water for it to clump around. So what you're looking for is a small excess of the sodium sulfate to look the same in the bottle or in your liquid as it does in the reagent bottle where it was dry to begin with. Okay, it's harder said or harder done than said, one of the above. Okay. To prove that you did a good job, we're going to do a couple different things. One, you're going to calculate a percent yield. 2, you're going to run an IR. And 3, we're going to do a chemical classification test. The IR identifies bonds. Okay? That assumes our bonds changed in the process of forming our product. We lost an alcohol, we formed a double bond. You should be able to look at these two forms of two spectras and identify which one's your product and which one's your starting material. As far as the chemical classification test goes, this is one that you should have all seen in lecture. Okay, the addition of bromine to a double bond. Bromine is red. Your starting material is clear. The product of, or the dibromocyclohexene product is also clear. So how do you know you made your product? What happens when we add the bromine to the solution? If it changes color, that means bromine's not reacting. What happens if it, sorry. Yeah, if it stays clear, it depends which liquid you're looking at. If it stays clear, the bromines reacted with the material, whatever material it was that you made, which in theory should have been your product. If you go through that whole process and you end up with some weird liquid at the end and you add bromine to it and that solution turns brown, what does that mean? You didn't have the alkene product, or at least you didn't have an alkene. Okay? The very end of this would be concluding everything. I'll let you read over that because I don't think it's all that important. But I didn't say that on record. Actually, I think I did. We'll go ahead and move to the group activity. Most people had problems with the very last two questions. We won't grade the very last page. Every other page will get graded. Okay? If you've got questions with the mechanism, please ask. Based on this morning's experience,